Hello everyone, my name is Yepeng Pan. I'm glad to present our work, Reliable Payload Transmission past the Spoofed TCP Handshake. Well, our work concerns TCP spoofing, which is the attack to establish and use an IP spoof TCP connection. So, the motivation of a TCP spoofing attack is usually to evade IP-based authentication or block listing. Here we provide several examples. For example, in the emailing system, we use the sender policy framework to verify if a connected IP is a loud sender of a domain. Also, some database, for example PostgreSQL, may verify a connected user by the IP address. In firewalling, the administrator may sometimes allow list a certain IP range to access sensitive data. All these are potential use cases of a TCP spoofing attack to try to evade IP-based authentication. To perform a TCP spoofing attack, we have two stages. The first stage is that the attacker wants to establish the connection. In the past, this is possible by predicting the server initial sequence number, i.e. ISN. Well, but now operating systems has improved the ISN generation to avoid predicting. Another chance of the attacker is that he could try to brute force the server ISN. That is, as you can see here, the attacker spoofed the source IP of a victim and then sent the IP spoofed SIM packets and a flood of IP spoofed ARC packets to try to acknowledge the server's ISN number. Once successful, a spoof connection will be established. After the first phase, the attacker now needs to use the spoof connection. To use the connection, the attacker needs to build packets with a sample and valid ARC values. But since the brute forcing part is blunt, the attacker doesn't know when the connection is established nor what is the correct ISN number used by server. So how could the attacker use a spoof connection? We started how could the attacker use a brute force TCP connection to transfer payloads after the handshake phase. And we're going to introduce two attack primitives. The first is to brute force the send window of the spoof connection. And the second is to use feedback channels to acknowledge server ISN to the attacker, so the attacker can learn the server send window and use the connection. Let's look at the brute forcing send window first. So, according to RFC, for an established connection, ARC numbers satisfy the following condition are stable. And we visualize this formula here. As you can see, we have one pointer send next, which is the next byte to be sent. And we have another pointer send unacknowledged, which is the first byte sent but not acknowledged. And upon receiving a segment, if the ARC value of the segment is after send next, so we reject the packet because the packet is acknowledging something the server has never sent. And if the packet ARC value is before send unacknowledged, then the server considers it as an old or duplicate ARC value, but may still accept it as long as it is not too old and within the range of max send window. However, the current standards do not forbid old ARC values that can acknowledge data the server has never sent, and we call them as ghost ARC. This happens for newly established TCP connections. Let's consider that now we have send unacknowledged equal to send next equal to ISN number plus 1. In this case, according to the previous formula, the server still consider ARC numbers before the ISN as acceptable old ARC values. However, because this is newly established connection and the server has never transferred any data, the server has never used these ARC values before ISN number. Such a permissive window checking allows an attacker to inject payload into a newly spoofed connection. And to do so, the attacker simply splits the whole searching space into equal window-sized pieces and try one ARC number per piece, and then one package will be accessible to the server. Because the existence of window scaling, the max window size can be extended to 1 GB, and at that time, only 4 attempts is able to inject a payload. The attacker could, so to use such a ghost ARC thing, the attacker could launch the TCP brute forcing to establish connection together with the TCP brute forcing to inject the payloads. Once the spoofing part is successful, the in parallel running send window brute forcing can inject the payload into the connection. We verify the behavior in several different operating systems, and it appears that Windows, BSD, and Linux, they all accept GoStack. And Linux already patched the issue in upstream. And we also reported the problem in IETF's yearly meeting, and is now working towards the internet draft to improve the ARC validation. So now we have introduced the first attack primitive to brute force the send window, but notice that such a send window brute forcing is still not aware of when the spoofing is successful, nor what is the correct server ISIN. As the second attack primitive, I'm going to introduce the feedback channels. These feedback channels can acknowledge correct server ISIN to the attacker, so the attacker can learn the server send window and use the connection. The first feedback I'm going to introduce is based on synchrony. In Linux, for a listening socket, the kernel maintains a SYN backlog queue to record received SYN packets. As you can see here, when the queue is not full, upon receiving new SYN packets, the server keeps it in the backlog queue and then send the normal SYN ARCing response. While if the queue is already filled, upon receiving new SYN request to counter SYN flaws, the server stops, records it in the queue, and will send the SYN ARC package with SYN cookie in response. So normal SYN ARC and SYN cookie SYN ARC generate ISIN numbers in different ways. And in short, the generation of ISIN number is both a hash computation over the address tuple plus a clock counter. But in the normal ISIN case, the clock counter is updated per 64 nanoseconds. And that is to say, if the attacker sends SYN packets from the same address tuple, it should say the ephemeral ISIN number because the clock counter is updated very frequently. While in the SYN cookie case, the clock counter is only updated per 1 minute. And that is to say, if the attacker again sends SYN packets from the same address tuple, it should say non-ephemeral ISIN numbers. By observing the ISIN generated, the attacker can now infer if SYN cookie is active. Recall that in the previous slides we said SYN cookie is only active if the SYN backlog queue of the server is filled, and then the attacker can source by checking the ISIN number, infer if the backlog queue is filled or not. So how could the attacker do this? Consider the following setup. We have an attacker, a victim, and the server. The server has a listening socket of backlog queue less full. Now, the attacker sends full connection requests to try to fill the queue, and one of the connection requests is using the spoofed IP of the victim. The attacker will try to establish the connection in the future. Because the queue is full, if the attacker now uses SYN packets from the same address tuple to probe the queue, it would find that the server reports non-ephemeral ISIN number because SYN cookie is used. Then the attacker tries to send the ARC packets to try to establish the spoofed connection requests. When the spoofing is not successful, the connection request remains in the queue and the attacker probe should still reveal SYN cookie ISIN number. While if the connection is established, and the established connection will be removed from the SYN backlog queue, and now the backlog queue is not filled, if the attacker again uses SYN packets to probe the server, it would find non-SYN cookie ISIN, and such a difference between the ISIN numbers tell the attacker a connection is established and which ARC number established the connection. So we performed the experiments in both local and remote setup, and to conclude, the feedback channel can acknowledge exact correct ISIN number in 50 and 70% chance in local and remote setup. These inaccuracies are mostly caused by different types of noise, and the first type of noise is network, basically packet reordering and packet loss. Let's consider that we have a we have a backlog queue with one empty entry. So according to the feedback we just talked about, if the attacker now sends SYN package to probe the queue because SYN cookie is not active, the attacker should see ephemeral ISIN number. But if packet reordering happens, for example, we might have the reset package to be delivered before the SYN package, and in this case, the first connection requires survival in the queue, and the second connection request from the same address tuple simply trigger a transmit of the SYN ARC packet, and that will produce the same ISIN number. So such a noise could delay the acknowledgement of successful spoofing attempts because we see the ISIN is not changing. But such a noise can be fixed by later reset packets in later probing sequence. Packet loss also have a similar effect. Consider that we simply drop the reset packets here. The second noise source is coming from user connection request. When the spoofing process is not successful, the SYN backlog queue remains full, and this time the legit user connection request doesn't have an effect because our SYN probes already reveal the queue is full. However, if the connection is established and if the user request comes before the attacker SYN probe, then this time we have client connection noise. So this is because our SYN probe will still reveal the queue is filled, and until the user connection request is established or timeouts and removed from the queue, we still don't know the connection is successfully established. The last source of noise is SYN cookie itself. So because as we said, SYN cookie is also not perfect static, it is also updated per every 1 minute. And if two SYN probes are sent at the blink of a 1 minute time frame, we might see different ISIN number. But this problem is easy to recognize because later probes will still show the same ISIN number, and we know it's such a ephemeral ISIN number is caused by SYN cookie time shifting. So we now have introduced the first feedback channel based on SYN cookie. Next, I will introduce feedback channels based on application specific, based on specific application. And such a feedback channel is only possible if the attacker targets a particular server running particular TCP applications, but it can always acknowledge the successful spoofing and the exact correct ISIN number. So I will talk about the application-specific feedback channels in the simple mail transfer protocol. The simple mail transfer protocol is used by email servers to deliver emails in the network, and as a defense against spams, mail servers usually use the sender policy framework to validate if a connected IP is a legit email sender for the specified domain. As you can see here, it's a normal SMTP session between the client and the server. The client needs to specify who is the sender of the email and the sender domain. So upon receiving these commands, the server then resolves the DNS records of the specified sender domain, and it found that indeed 1111, the client's IP, is a loud sender of the sender domain. Well, in a TCP spoofing attack, the attacker could spoof the IP low-listed IP and then try to send spine that can pass the SPF check. So the DNS lookup behavior of SMTP servers actually introduce potential feedback channels. Let's consider a normal TCP spoofing attacker. It tries to spoof the source IP of the victim and then sends IP spoofed SYN packets and ARC packets. But this time, in each of the spoofed ARC packets, the attacker pitch back a payload, and the payloads unbinds the ARC value together with the attacker domain in the mail from command. And when the connection is established, the payload in the corresponding ARC package will be accepted by the victim server, and the server needs to resolve the DNS records of the specified domain. And that time, the attacker could find the ISIN number from the incoming DNS query. Not only DNS, email itself, it also provides a feedback channel. There are plenty of public email servers, for example, like Gmail, Outlook, and the attacker could also register their own email address. For example, now we have attacker@gmail.com. And this time, during the spoofing process, the attacker slightly changed the payloads, and the payload aims to deliver an email to the attacker-controlled mailbox. And the ACK number can be embedded in the subject or body of the email. Once spoofing is successful, the server will deliver the email to the attacker-controlled email box, and then he could say the attacker could extract the correct ISIN from the email received. It is not always possible that the attacker could register an account on the target server, and in these cases, the attacker could try to rely on bounce message. So this time, the attacker needs to set up its own mail server. And also the payload is slightly updated, where the mail from and by the attacker, the ACK package together with the attacker domain. And the recipient of the email is targeting some not existing address, or it can simply targeting an address with auto reply setup. Upon the server established the connection, it consumed the payloads and found that the email cannot be delivered and will try to send a bounce to the sender. And this time, the attacker also knows the ISIN number from the incoming email. We tested prevalence of the feedback channels, and against the top 10K domains with an email server, there were at least 25% of all these email servers susceptible to at least one of these feedback. To summarize, in this talk, we studied how could the attacker use the spoof TCP connection, and basically to attack primitive. The ghost ACK allows the attacker to brute force the server send window, and the second is feedback channels can acknowledge the server ISIN to the attacker, so the attacker can learn the correct server send window and use the connection. Here are the references we used in our presentation. Thanks for your attention.